why don't we go over what we did before, kind of look at what we've been doing, and then we'll start on new stuff. Okay, so with these notes, we're doing related rates, which are just word problems involving derivatives, right? So we have a little strategy to do these questions. The first part of our strategy is to draw some sort of diagram. Okay, so just draw something to help you out. Number two is to introduce some notation. So make sure that any variable that you use has an explanation for it. Third, I wanted you to express everything in the question in terms of derivatives. So if you're given a change in something, turn that into a derivative and make sure that the signs work out. Finally, you're going to write an equation that relates all the quantities together, either using like the Pythagorean theorem or the geometry of the situation. Number 5 is using implicit differentiation to solve for what you want. And finally, step 6 is plugging in everything that you're given and including things that it wants you to find. Okay. So we did a few examples on related rates. We did some easy examples where we have like a shape that's increasing, and that was pretty easy because everything was positive and we were given the equation, so it wasn't too hard. Then we talked about what happens when things are decreasing or maybe going down, or decreasing. And that kind of introduced the idea of putting negative numbers in what we're given in the question. So for example, if a snowball is decreasing, then that means its surface area is going to be a negative derivative. Okay, so I talked about that. Last class, we also were introduced to questions that didn't give us an equation. We had to come up with it on our own. And we used the Pythagorean theorem to do that as well. So we're combining theorems that we know and negative and positive values as well. So we did a few examples like this. Now we're going to do something a little bit different. So we have 2 more word problems to get through, and then maybe we'll call it a day. So let's take a look at example number 5. Okay. In this example, we have a car. Car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Okay, they're both headed for this intersection where the 2 roads meet. And we want to know at what rate the cars are approaching each other when car A and car B are a certain distance from the intersection. Okay, so step 1 says we have to draw a diagram. Oh, I almost wrote step 4. Okay, so we have a car traveling west and a car traveling north, which means I guess we have a road that's going vertically and a road that's going kind of horizontally, right? Okay, so I just kind of drew my roads here. Since car A is traveling west, I guess it's on the horizontal road. So this must be car A. And that's got to be traveling west. Okay, now car B is traveling north. So car B is going kind of upwards. Okay, now they're both headed for the intersection in the middle. Okay, now what we're interested in is how fast the cars are approaching each other. How can I write that in my diagram? Or how can I draw that? So maybe the distance between the cars themselves.
Make it a right triangle.
Yeah, make it a right triangle. Maybe connect the 2 dots here. And that diagonal line represents the distance between the 2 cars, right? Okay. Let's go to step number 2. Yeah, it would be the hypotenuse. Okay, so we have several variables to go over here. Let's see, we're talking about distances, right? Now, maybe we should talk about the distance between the 2 cars themselves. So maybe this hypotenuse, and I don't know, what do you want to call it? What do you want to label it?
C.
C, okay, that works. Let's label that C. And on step 2, I'm just gonna make sure I write that out just so I don't get confused as I continue. So C represents the distance between the two cars, right? Okay. What other distances are we given in this problem? What else?
The distance between the intersection for A and B.
Yeah, right. The distance between car A and the intersection and the distance between car B and the intersection. Why don't we label those A and B since we have C already, right? So maybe A is the distance between car A and the intersection. So I'm going to write that one out. A is the distance between car A and the intersection. Okay, and I guess car B or B would represent the distance between car B and the intersection. Between car B and intersection. Okay. Now, I honestly don't think we have anything else to label here. I think we've got everything that we want in terms of distances. So let's move on to step number 3. Step 3. Okay. Step 3 asks us to figure out what we're given and then what we want in terms of derivatives, right? So let's take a look. What is the question giving us in terms of derivatives? So just reading the first sentence, car A is traveling west at 50 miles per hour. How can I write that in terms of derivatives? Sam?
Since we're talking about distances, then velocity or the speed would be the derivative of that.
Good, so it'd be dA, right, over dt. And that would be, what, 50 miles per hour? Now, let's talk about the sign. Car A is moving west. Do you think the distance between car A and the intersection, do you think that's going to be decreasing or increasing? Decreasing, right? As car A moves to the left, it looks like the distance between car A and that point in the middle is going to be decreasing. So it looks like this derivative is actually going to be negative, okay? Because the distance between A and the intersection is getting smaller. Okay. Let's look back at the question. It says car B is traveling north at 60 miles per hour. So I'm guessing that might be dB dt, right? So 60 miles per hour. And what do you think the sign on dB dt should be? Positive or negative? Ooh, what's the distance between car B and the intersection doing?
Right.
Car B is rising, but what is the distance between here and here doing?
Shrinking.
It's shrinking, right? And let me show you, let me make it a little bit more obvious here. As time goes on, car B is going to get here, and it's gonna go here and go here and go here, right? And as it continues to go through time, car B is actually getting closer and closer to the intersection, which means that it's actually decreasing that distance. Do we kind of see that?
When we do these, would you want us to draw like a coordinate system or no? Is that not necessary?
What's a coordinate system?
Like basically showing what positive X and positive Y are.
Oh, you mean like being, okay, like this is like my axis and this is
Yeah.
positive. No, that's fine. You don't need to draw it. If it's helpful to you, then go ahead and draw it, but I'm not looking for that. All right, so I think we all agree that both of these derivatives have to be negative because the distances are both decreasing. Okay, I never heard it called a coordinate system. Huh. All right, let's talk about what we want to find. Okay, as we read further into the question, it's asking us, at what rate are the cars approaching each other? Now, I guess that's telling us to figure out something about C and specifically how fast C is changing. So it looks like we do want to find dC dt, okay? And very specifically, it wants us to find dC dt when car A is 0.3 miles from the intersection. So I guess when the A or the distance between A and the intersection is 0.3 miles. And when B is 0.4 miles from the intersection. Okay. So we could do a little bit more work on step 3, but I'm actually gonna continue on to step 4 and see if we ever need to go back. Okay. Step 4 says we need to find some sort of equation that relates all our variables together. Can someone give me an equation that relates A, B, and C together? Yeah, right. It's a right triangle. Looks like the Pythagorean theorem is going to go along here. So A squared plus B squared equals C squared is definitely something that we're looking at. Okay. Well, that was easy. Let's go to step number 5. Step 5 says we need to take the derivative of my equation. Let's do it step by step. What's the derivative of A squared with respect to T?
2A
Times.
times dA over dt.
Perfect. Okay. And I think it's pretty obvious what the other ones are going to be, right? Plus 2b dt. Oh my gosh. And then the last one's going to be 2c dt. Oh my gosh, dc dt. Okay. So that was pretty easy. Seems like we want to find dc dt. So maybe I should solve for that just to make things easier for us. So I guess we need to divide by 2c. Okay, now just to make things a little bit more simple, I'm going to divide each term by 2c. So this becomes 2a over 2c dA dt plus 2b over 2c dB dt, and dc dt is by itself. Okay. And just to make things a little bit easier, we can cross out the 2's, right? So this becomes A over C dA dt plus B over C dB dt equals dC over dt. Okay. So it looks like I have what I want to find already. I guess step 6 is plugging in what we know, right? Okay. So in step 6, we're going to plug in dA dt as -50, dB dt as -60, A as 0.3, B as 0.4. Wait, but I have to plug in C as well, but the question didn't give me C. Any ideas on how we can get C, Zach?
Plug in A and B into A squared plus B squared equals C squared.
Perfect, right? I know that A squared plus B squared equals C squared. I know what A and B are. Maybe I should figure out what C is. Okay. Now, just to make things a little bit easier on me, I know that C is the distance between the two cars. I kind of already know that's going to be in miles, so I'm not going to use the units in here when I do this. So I'm just going to do 0.3 squared plus 0.4 squared equals C squared. 0.3 squared is 0.09. 0.4 squared is 0.16. And we have C squared. When I add these together, I think I'm getting 0.25 for C squared. So the square root of 0.25 is 0.5. So I know that C is 0.5 miles since we're doing distance. Okay, so just quickly on the side, I figured out what C was going to be. Okay, now it looks like I can plug everything in that I need. So I'm going to go ahead and do that. So A over C becomes, let's see, 0.3 miles over 0.4 miles. dA dt is -50 miles per hour. Then we have plus B over C. B is 0.4 miles. C is 0.5 miles. Oh, did I make a mistake here? Yeah, C is actually 0.5 miles, right? Not 0.4. Sorry about that. There we go. That looks a little bit better, right? Okay. dB dt is -60 miles per hour. Okay, and that's what dC dt is. Okay, So let's see if we can do this. I'm gonna kind of cheat, and I did this in my calculator already. I know that 0.3 over 0.5 times -50 is actually -30. Okay. Now, just looking at the -30, what should be the units on that specific value? Miles per hour, right? Because the miles cancel out and we're just left with miles per hour. Okay. Next, I can add on 0.4 over 0.5 times -60, which I already did in my calculator, and I got -48, also miles per hour, because the miles cancel out. And when I add these two together, when we add units, they kind of just stay the same if we have the same units together at least. And when we do this, we get -78 miles per hour. And this is my final derivative. Okay. So in terms of the question, the two cars are actually approaching each other at a rate of 78 miles per hour. And it actually makes sense that we have a negative derivative because the cars are getting closer.
What are the miles on the bottom of the denominator?
Where are the miles on the denominator?
Because it's 0.5 miles in between both.
So here. So where are the miles?
Oh,
Yeah, the miles.
okay.
Yeah, I think you might have done everything at once, which might be the reason why you canceled it out. Yeah. All right. Nice question there. Any questions on example 5? All right. If you flip the page over to example number 6, I have a very similar example, but the cars are going different directions.
So cars there.
Instead of cars, it's Jacob and Bella running towards each other, trying to get to the baby. All right, I'll give you a few minutes to work on this, and then we'll come back in a tiny bit. I think I'm gonna go over this, and I'm sorry that I haven't been making you write stuff on the board lately, but I do want to go through this in a step-by-step method instead of just doing the problem, because I think it makes it a little bit easier to understand. So I'm just gonna go through this as a class, but let's read through this question real quick. So we have our nice Twilight example. Jacob is running east at 90 kilometers per hour, which is really fast, but remember that he's a werewolf, so that's okay. And then Bella is running south at 60 kilometers per hour, and that's okay because she's a vampire, right? Okay, so if I'm drawing this example, let's see. We would have Bella running south. Okay, maybe I can draw her. Okay, and then we got Jacob running east. Okay, and he's a werewolf, so we gotta draw that. It's really important. Okay, and they're all going to Renesmee, who's in the middle, who's the Loch Ness Monster. There we go. Okay, that makes it a little bit more. It's very necessary to the question to draw this. Okay, talking about variables, which is step 2. Okay, I think I saw a lot of people using different variables, which is fine. What should I use with the distance between Bella and the intersection? What did we use for that one? Or like what variable would we use? Okay, I like C's okay. Maybe I'll use B just because Bella's name starts with a B. So I know you use different variables, but I'm gonna have B be the distance between Bella and Renesmee. Okay. Now the other distance is Jacob, but between the Loch Ness Monster as well. I think I'm going to use J just because we're using the first names. I know that some of you have been using like X and Y, A and B. That's totally fine. But I'm going to have J be the distance between Jacob and Renesmee. Okay. Just like the last example, we're asking about the distance between the two cars or between Jacob and Bella. And that would be the diagonal distance, right? What did you guys use for the diagonal distance variable? C works for me. Okay, so C is the distance between Bella and Jacob. Okay, so we have our three variables going on. Let's move on to step 3, which tells us to put everything in terms of the question. Okay, so first of all, we have to figure out what we're given, okay? Let's go to the question. Jacob is running east at 90 kilometers per hour. How can I write that in terms of the question? Or in terms of derivatives? And that's going to be 90 kilometers per hour. Is this going to be a positive or a negative derivative? Negative, right? Because as Jacob is running east, the distance between him and the intersection is getting smaller, right? So if we're decreasing, then we need a negative value. Okay. Now, the same thing goes with Bella running south. As she runs south, the distance between Bella and the intersection is getting smaller as well. So that means that dB dt is going to be a negative value, and it's going to be 60 kilometers per hour. Okay. Next, we want to find out what we want to find. We want to find at what rate Jacob and Bella are approaching each other, which is the distance or the change in C, right? So we want to find dc dt, and more specifically, when Jacob is 0.2 kilometers away, so J is 0.2, when B is 0.15 kilometers, and I want to find the distance between them and how fast that's changing. Okay, let's go to step number 4. Okay, can someone give me an equation that relates all my 3 variables? Good, I think I heard it. B squared plus J squared equals C squared, right? Pythagorean theorem, same thing as we've been doing as before. Okay, now I would ask you to find the derivative with me, but we did do it in the last example. So I think we can all agree that the derivative of this is 2b dB dt plus 2j dj dt equals 2c dc dt. Okay. All right, we want to find dc dt, so it looks like we're going to have to solve for dc dt, which means I need to divide everything by 2c. Okay, so it looks like we're left with 2b over 2c dB dt plus 2j over 2c dj dt equals 2c over 2c dc dt. Once we're here, looks like we can cross out some 2's. So we're left with b over c dB dt plus j over c dj dt equals dc dt. So what we want to find is by itself. So that means we can move on to step, I know I skipped writing step 5, but step 6, which tells us we can substitute things in. Okay. So it looks like I can plug in dj dt, dB dt, j and b, but we do have a c there. How do I get c by it? Or how do I get c? Pythagorean theorem, right? I know that b squared plus j squared is c squared. So that means 0.2 squared, or 0.15 squared plus 0.2 squared is c squared. And I'm going to skip a couple of steps here since we did do a very similar example before. This should give you that c is 0.25. Is that what everyone got? Good. That means I can go in and substitute some values. B over c gives me 0.15 kilometers over 0.25 kilometers. dB dt is negative 60 kilometers per hour. Okay, and I'm adding on j over c, so 0.2 kilometers over 0.25 kilometers times dc dt or dj dt, which is negative 90 kilometers per hour. Okay, now I'm going to skip doing all the calculations. This should give you negative 108. Okay, what should my units be? Kilometers per hour, right? Because the kilometers cancel out and we're left with kilometers per hour being added together. Okay, so the two are approaching each other at a rate of negative 108 kilometers per hour. All right. Any questions on example 6? All right. Now, one thing I want to say about related rates is these questions actually get exponentially harder. I haven't asked you anything too bad with related rates. These can get very much more difficult. I'm not going to do those in this class. If you are interested in doing more complicated related rates questions, talk to me and I'll give you some. But I think I'm going to leave it here. But if we don't have any questions about this, then I'll let you go a little bit early. I'll see you tomorrow. We'll do a game. It won't be a speed game, so we'll do some slower review questions, and I will see you tomorrow.